So, thank you for the introduction. It's a pleasure to be here, and thank you all, first and foremost, for being here. So, without further ado, let's start. Maybe some very quick notes. I would say that Michael has already introduced me very well. So, I'm one of the security researchers at Nozomi Networks Labs. I have two main responsibilities basically in my job. That is, one is break devices, and secondly, unfortunately, but still, it's part of the job, have long discussions, very long discussions with manufacturers to have them fixed. I'm responsible for 38 CVEs in the last 2 years, but others are still upcoming. And, well, we already know, the talks that I've done so far. But what about today? Today, we're going to talk about BNCs, those devices that are not very well known in OT and IoT devices. So, I will start with an introduction on BNCs. We'll continue walking through all the steps of our research. We'll show you a complete attack demo that ends with the disruption of the industrial process. And then we'll finish with a summary and some key takeaways. So, first and foremost, let's start with some background on the Purdue model that might be obscure to all of you that don't work directly with industrial control systems. So, the Purdue model is a reference architecture that divides an industrial network into basically 5 levels. There is also a 6th level in some diagrams that is called level 5, but still it's pretty much like this. So, we will find at level 4 and 5 the enterprise IT network, maybe some business planning and logistics. So we will find devices such as email servers, cameras, printers, etc. Then we have an upper demilitarized zone that is the transfer network between IT and OT devices. Then we have an operations network that is the first OT network. And here we will find systems that provide IT services, such as, for instance, the DNS to the lower levels, and that collect historical data, so for instance, historians. Then we have a level 2.5 network, that is the lower demilitarized zone, that is optional actually. Then we find the first process network, so we'll find systems that use those IT services from the level 3, and that control or acquire data from the lower level. So we will find engineering workstations, human-machine interfaces, etc. Then we have the level 1, so systems that collect and transmit data to the field devices. And for instance, we'll find programmable logic controllers, RTUs, DCS, etc. And finally, the field network, that is the network that contains the actual sensors and actuators that are that control and monitor the industrial process that we want to control. So, given this clear segmentation, it's easy to understand why this model, although being more than 30 years old now, has been and is still adopted as a cybersecurity reference model. But during this presentation, we will see how this model will be severely tested. But now, let's talk about these baseboard management controllers, or BMCs. So, what exactly is a BMC? It's a supplementary system on chip designed for the remote monitoring and management of a computer. It is tightly coupled with the hardware in order to allow to perform low-level operations on systems completely remotely. It is either embedded in the hardware motherboard or sold as an optional expansion card, and famous brands embedding BMC solutions are ASUS, Dell, Gigabyte, so many of those. So, in this slide, I projected the specifications of a BMC from ASPEED, which is a popular manufacturer, and you can clearly see that it is basically a PC within a PC. It has its own CPU that is usually ARM-based. It has its own RAM. It has its own VGA controllers. They even develop VGA drivers for many hours, because a BMC, well, most BMCs are able to provide basic graphics capabilities to the host, to the managers, the staff, so that even if it doesn't have a graphics adapter inside, is still able to provide a graphics output. Its own LAN, its own flash memory, so it's basically a fully fledged computer. And well, let's see now a block diagram of a motherboard that is equipped with a BNC to understand the interconnectivity and what the BNC can control. So let's focus now on the BNC. And you can clearly see that that in this schema, this, for instance, first and foremost, is connected through the PCI Express lines to the CPU. It is connected to the M2 slot, so to the hard drive of the host. It is connected to the Ethernet interfaces that are being used by the host. It provides its own management LAN. It has the VGA output or an HDMI output, whatever, a communication port. And it's also connected to the USB bus of the system. But what exactly can a BNC control with respect to the host? So, on this slide, I put on the left a list of capabilities that are provided by a BNC, and on the right, how appealing they are to a hacker. So, we will start with some hardware monitoring capabilities and logging of events regarding to this monitoring. So, we can monitor the temperatures of our host, the voltages of various components of the motherboard, the power loads, the fan speed. We have an inventory of device paths, which is, interesting, but still not really much. But then, we can consider that BNCs can also provide a remote system power control that is power off, reset, or even power on a host. An important thing to remember of BNCs, as a matter of fact, is that as soon as you plug a device that is equipped with a BNC, the power network, the BNC goes on and stays on all the time. You are not supposed to shut it off. You cannot even shut it off. It doesn't provide that feature. So it's always on, and that's exactly why it allows you to turn on the managed device. It can provide screen recording. Well, it has its own graphics adapter, so why not just record the output of this graphics adapter? It can provide keyboard and mouse interaction straight from the bootstrap. That is, we can even enter the BIOS setup and change settings through the BNC. And we can even remotely mount CD or DVD images or HDD images that would appear to the host as if they were directly connected to it. But finally, we can also reflash the BIOS and the BNC firmware many times from the BNC itself. So you can immediately understand how powerful this device is. Okay, so let's now do a recap of the normally exposed network services by a BNC. So for sure, it has a web interface that is one of the main services by which you're supposed to control your BNC. It has this IPMI service that stands for Intelligent Platform Management Interface. It's a sort of service by which you can send commands through a basically command line interface. For instance, in this case, this screenshot depicts the usage of IPMI tool, by which we can send command to the BNC and we can either acquire data from the host, such as here, or we can issue commands that control the host. It provides an SMP service, no big deal here, nothing new. It provides this KVM service, but mind you, here, KVM does not stand for kernel virtual machine, but stands for keyboard, video, mouse. This is a sort of evolution of BNC, basically. It allows you to not only to have keyboard and mouse interaction, but also to mount those media as it was anticipated. And finally, some BNCs also have an SSH interface that usually grants you access to a restricted shell. Okay, so far we have seen a generic BNC. Let's now talk about a specific solution that is the American Megatrends Megarack SPX. So what is the Megarack SPX? It's AMI software or firmware solution for BNCs. It is almost an operating system that is developed by AMI and specifically for BNCs. It features all the services that we have just mentioned, so the web interface, with Redfish API support, which is a standard set of APIs by which you can control multiple BNCs. It supports IPMI, supports SNMP, KVM, etc. To the best of my knowledge, this is closed source. There is also an open source version of this BNC software, but it's based on OpenBNC and it's completely different than the SPX version. And each OEM can decide to customize it according to its needs. So, how common is the AMI Megarock SPX? This lab collects a few OEMs known to use it in their own products. So, ASUS uses the Megarock SPX in its ASMB10 IKVM solution and many others. Dell was found using the Megarock SPX. Dell is famous for its own iDRAC solution that provides more capabilities, etc. But still, for some devices, it has chosen the Megarock SPX. Gigabyte uses the Megarock SPX. Hewlett-Packard, again, uses the Megarock SPX. The situation is pretty much the same with Dell. So Hewlett-Packard developed its own integrated lights-out solution, the ILO. But still, for some devices, it has chosen the Megarock SPX. Lenovo uses the Megarock SPX. NVIDIA was found using the Megarock SPX. So, I mean, it is pretty common. But one important thing to mention is that all these OEMs embed BNCs in mostly IT solutions. Recently, this is changing. So here is Lanner. Lanner is a popular manufacturer of embedded solution, of industrial automation solutions. And guess what? If you look at the documentation on its own website, you will find the Megarock SPX inside their own product. Or here is Tyan. Tyan is another popular brand that is under the Mytek holding group. And it has its own branch that develops embedded solutions that target, for instance, IoT, telecommunications, networking, industrial automation, military, medical, and healthcare. And guess what? Here it is. Here is the Megarock SPX, again, in their own products. Now, you remember the Pujol model, right? So, let's keep the Pujol model on the left of this slide. Let's put the BNC block diagram on the right. Let's imagine for a minute that the device of this block diagram is an OT device, and let's focus on the network interfaces. So, regarding the 2 GB interfaces, if this is an OT device, those will be found connected to the level 3 or level 2 networks. But now, what about the management LAN? It is actually customary to find it connected to level 4 because, after all, the BNC is used for monitoring and management purposes, so it is mainly used in IT tasks. Thus, it becomes absolutely important that the BNC is as protected as possible, because if that is not the case, considering all the functionalities that the BNC provides and the possibility to deeply control the host, the BNC could be easily abused to jump from IT to OT networks. So, over the course of the last year, we have conducted a research on the security of BNCs focused on OT and IoT devices. And here at NOHAT, we anticipate the first results of our analysis. So, this is the first bunch of vulnerabilities affecting the Megarock-based BNC firmware of OT and IoT devices. As you can see, there are 13 vulnerabilities, and 5 of them are rated critical. In the next section of this presentation, we're going to walk you through our research methodology, in-depth describe a subset of those issues, because we don't have the time to do all of them, and present their impacts. And as you can see at the bottom, there are also other vulnerabilities still to be released. Unfortunately, they're still in the process of to be fixed, and as such, we cannot disclose them right now, but stay tuned for updates later this year and in the next year. So, first and foremost, let's analyze the device that we used. Let's describe a bit the device that we used for our analysis. So, during our research, we analyzed a Lanner NCA5220A, which is a Rackman appliance that can be configured for industrial applications. But more specifically, we focused on the IAC AST2500 module, that is the expansion card that provides BNC capabilities. As anticipated, some brands decide to offer BNC capabilities through an expansion card. Here is one case. And its firmware is based on the AMI Megarock SPX. So, as a reminder, the determining factors of the possibility to easily assess the security posture of a system are the firmware availability. So, how easy is it to obtain the firmware? The firmware observability, is it possible to analyze the firmware or are there any obfuscation steps? And the device accessibility, so does the device allow to be inspected? Now, as for the firmware availability, it is not publicly downloadable from the official website. However, Liner readily shares firmware images to customers, so just simply by asking them via email. So it was an easy task here. In terms of observability, apart from the installation of the required dependencies, again, this simply resulted in one firmware command. So the entire firmware file structure was extracted, and it was possible to browse all files of the custom Linux operating system. It was the device accessibility that proved to be the trickiest point, as no SSH remote access was allowed. The only exposed services are basically SNMP, HTTPS, IPMI, DHCP, and an unrecognized one which turned out to be systemically related. This means that either we proceed for a static analysis only, or we try to find an alternative way to dynamically debug the device, for instance, by reverse engineering the firmware and modifying it to add debugging functionalities. In this specific case, we decided to start with a static approach and then invest the time for a dynamic approach only if necessary. So, the web application is usually a juicy target and seemed to be the most promising service of all of one. So we started analyzing it. And let's show here the login process. I mean, it's not particular difference. I mean, it's pretty basic. You enter the credentials, you wait some seconds for them to be processed by the BNCs, and you're in. So no big deal, right? Wait, but what was that dialog box? So if another user is logged into the same account that we want to access, the web application asks if we want to override that session. And this is implemented via an authenticated post request to API kill duplicate user. As a matter of fact, you can see the QSessionID cookie in the request. So, to my eyes, this looked exactly like one of those boring components that nobody tests because, you know, it's a dialog box. What could possibly go wrong with it? Well, let's find out. So, if you recall from a previous slide, AMAP identified the server running on the device as LTTPD. And a look at the COM file revealed that requests to API are handled by this SPX REST service, this binary that is responsible for all API interactions. And the kill duplicate user handler is registered by the MISC function that is called during the main. And this is how the decompile function begins. And, well, but where are the authentication checks? So, although the post request contains the QSessionID cookie, the kill duplicate user does not validate it. And you can clearly see it by comparing this function with others that are defined in the binary, where both checks on the session cookie as well as in the anti-scissor token are present. I mean, this already means that an unauthenticated attacker can perform denial of service attacks just and by arbitrarily terminating sessions. But wait, that's more. So this is how the function continues. And I will pause here. Let you look at it for a few seconds. I hope that you're able to read the code. I'll wait some other seconds. 4, 3, 2, 1, before showing you this. So, oh my. So, the function first allocates a limited size buffer on the stack. You know what I'm going. And then it copies in that buffer an unbounded user controllable input that is the username parameter. And by itself, this is already non-authenticated thanks to the previous vulnerability. Stack-based buffer overflow, even in a poorly fortified binary. Of course we have. But of course, you have spotted the common injection point there. It is just now a matter of understanding how safe this curiously called safe system is. And well, this function is implemented in the libsafe system shard object, And apparently, the only security check is done on the length of the string, and by this curiously named check buffer overflow function. So no command injection specific validations are done. And finally, to make everything worse, all processes run as root on the device. So, in short, by chaining all these vulnerabilities, misconfigurations, and failures, an unauthenticated root remote code execution can be obtained. All of this because of a better program confirmation dialog. Now, so we have compromised the BNC. The next step is to compromise the host. And there are many ways to do that. So the simplest one is by abusing the KVM or BNC service. So as we have the possibility to mount remote CD DVDs and interact with the host during the bootstrap, we can easily boot from a live distribution and do arbitrary operations on the hard drive. For instance, read files, bypass the lock screen, add malware, basically you name it at this point. However, this requires a reboot and the HTTP will be unencrypted, right? Well, if the BNC has direct memory access, those constraints can be bypassed as well. So here I've included a screenshot of this proof of concept developed for the HP ILO that by exploiting the direct memory access and some volatility code, it allows to unlock the Windows PC directly on memory. Now, for the sake of this presentation, I will show how this can be done using the KVM, as this approach would be extremely lengthy. And to abuse the KVM service, it is first necessary to understand how sessions are generated. The SPXRS service makes use of libq decoder for the session management. And you can see here, for instance, in the login function, the call to the qcgi/save function. And the libq decoder simply creates two files that are called .properties and .expire with the name of the session ID that has been temporarily generated for that session. And those by default are stored in the temp folder of Linux. So crafting a session is simply a matter of writing a new file following the same format. And this allows to bypass the login process and access the web application with admin privileges. So it is now possible to exchange this crafted session cookie for a valid KVM token. So here you can see a request where for sure the cookie and the sysserv token have not been generated by the web application, but in exchange for those, we got a very, very valid KVM token. Now, KVM access is granted, and the good old trick of swapping the CMD with the util mount to bypass the Windows login screen still works. So we can now have full control on the host and access the util device as well. Okay, so we have talked about a possible attack chain that an attacker can abuse to compromise the BNC, and we have discussed how to jump from the BNC directly to the host itself. Now, let's pack everything together and show how an attacker starting from an IT network can disrupt an industrial process in this demo that features our production line replica in our lab. So here is our production line demo. It is a faithful replica of real production lines. And as you can see, there are 4 cardboard boxes spinning on a plate that is being basically rotated by an electric motor that is commanded by a Rockwell controller. So on each box, there is a barcode tag. The idea of this production line replica is that the controller communicates with the barcode reader on the right, reads the barcode tag on the cardboard. If it is correctly read, it makes the motor spin to proceed to the next one. On the left, you can see the Lanner NCA5220, on which we installed the engineering software that programs the controller. So there are 2 interfaces, or you might see the 2 cables there. So one is the BNC interface that is connected to this mock level 4 IT management network, and the other is the host interface that is connected to the level 2 process network. So in our scenario, we will pose as attackers that are on the IT management network and want to ultimately disrupt this process. So we are now seeing the web interface of this BNC. We attempt to log in with the Haxer credentials, but of course this does not work. We don't know those credentials. However, we know that the BNC is affected by these vulnerabilities. And we have developed an exploit proof of concept that combines exactly the chain described before. And as you can see, our exploit requires only two parameters, our IP address and the remote target. So let's launch this exploit, and let's pause here and command what the exploit has done. So the goal of the exploit is to bypass the login screen by crafting a new session. And this requires writing the properties file and the export file. The write of the properties file is done in 3 steps due to those land limitations that we were talking about when we talked about the Ceph system. And at the end, the exploit verifies that it has succeeded, and if so, prints out the HTTP response that the attacker needs to use, replacing the legitimate one. This makes the client-side JavaScript code on the application that is running on the web browser of the attacker process the crafted session cookie as well as the anti-cserv token that were generated for this crafted session. So what we are doing now, basically, we are selecting this HTTP response. Okay, let's copy it. And now we go back to our web interface. We intercept this login request. We also intercept the response. And we replace this response with the one that has been generated by our exploit code that has, of course, previously generated the session on the server. And as you can see, we were able to completely bypass this login web page. Now, having done that, we go straight to the remote control functionality of this BNC. And you can see that here, through simply a web browser, we are able to directly interact with the remote server. Now, we're greeted by the Windows login screen. Of course, we don't know those credentials because we're attackers, we don't know this particular profile, but still, we can mount an ISO image. So we will mount the ISO image of whatever Linux distribution, and we will start the host. And as soon as it restarts, we start the media. Now, as you can see, we are seeing the Bootstrap live. That is what I was anticipating before. With the BNC, we can enter the setup. And so what we simply do at this point is just change the boot order to boot from our ISO image. And as you can see, the BIOS sees this ISO image as if it were directly connected to the host itself. And here we are doing the boot of the Linux distribution that we have decided to use for this specific case. And let's wait some seconds so that it loads. So we are still doing all the steps to a web interface that, as you can see, provides keyboard and mouse interaction, whatever. Now, having done the boot, we simply go to the storage of this device. We go to the Windows folder, to the System32 folder. Here we are. And we open a command there, a command shell there. And what we simply do is overwrite the utilman.exe, that is the service on Windows that provides accessibility functionalities, and that runs as system, in case you didn't know that. And we replace it with this classic CMD or Windows. So, having done this step, we simply reboot our system. We stop the media so that at the next boot, the Windows system comes out. We wait for a few seconds, and here we are greeted by the login screen of Windows. But now, if we press the accessibility button of Windows, we can obtain a system shell on the device itself. So now to bypass, well, this is just one of the possibilities. We could have done already a gazillion amount of things. It's just a way to compromise the host. So we create a new Hexer user, a backdoor user on this device, and then we just attempt to log in on this user. Oh, no, we are not interested in that. Thank you, Windows. Okay, so let's skip this part. And now that we have obtained complete control of the Windows user interface, what we do is that we launch the Rockwell software, the engineering software that allows to program the Rockwell controller. So, some seconds in order to allow him to boot up. And okay, so here it is. We do need to press the Go Online button because in this way we can directly communicate with the safety PLC of this demo. So we press the Go Online, wait for seconds, okay, we are now online. And what we want to do now is we go to the motor axis, we issue a motion direct command, and the idea is to issue a command to the safety PLC that overrides the current program that is being run by the safety PLC. So we decide to use a specific set of settings, and at the end, we press the execute button, And let's see what happened. And definitely it's not stopping. Definitely it's not stopping. Let's wait a few seconds, and here we are. So, as you can see, we were on the IT management network, and we ultimately were able, thanks to this chain of vulnerabilities, to disrupt this industrial process. This exact demo is still displayed fully functional at our booth, so if you have some time, please come and say hi, and we will reproduce this attack live for you again. Okay, so we are near the end of this presentation. So let's conclude it with a summary and some key takeaways. So first off, the Purdue model is still vastly adopted as an OT cybersecurity pillar, although it definitely starts showing its wrinkles, as you have seen. So besides being embedded in many OT devices, BMCs are rapidly getting popular also in the OT and IoT sector. We have revealed 13 vulnerabilities affecting the BMC firmware of OT and IoT devices, but others are yet to be disclosed. And we have demonstrated that by chaining all these vulnerabilities, misconfigurations, and failures, it is possible to compromise the BMC and the managed host, jumping from IT to OT networks. You've just seen it in the demo. To end this presentation, here are some actionable takeaways that I want all of you to remember and apply from now on in your daily work activities, especially if you work with this kind of devices. So, with the increasing connectivity of OT devices, new risk-based cybersecurity standards need to be adopted. The Purdue model used as a cybersecurity reference is more and more unable to keep up with the increasing connectivity of OT devices. Models such as the IEC 62443 that are instead risk-based are much better now at managing the security of newer and more complex systems. Care must be applied while porting solutions designed for the IT domain into OT environments, as the requirements greatly differ. As you all remember, the risk is the product of the likelihood with the impact. And if the likelihood is arguable, because it also depends on external threats, the impact for sure is going to increase while doing the jump from IT to OT, simply because of the safety dimension. Attacks on OT systems have physical effects on humans and on the environment, and as such, require much stricter security requirements to keep the risk manageable. And finally, an evergreen. There are attack surfaces that are little understood, but that have significant consequences if compromised. This presentation demonstrates once again that it is important to evaluate the entire attack surface and never focus only on specific parts, overlooking others. You could have applied the strictest security measures ever on the host, but this would have been completely useless due to a tiny chip embedded in your motherboard that maybe you did not even know it existed. Everything is important in security. So, thank you.